Hello and welcome to section 3, likelihood weighting. We ended up here that forward sampling has its own advantages, but when it comes to answering conditional probabilistic queries, then either of the ways, rejection sampling or separate estimators, they require a high number of particles. So how can we reduce it? Well, we can do that by setting the values of the event variables y. And we did this in the exact inference part. Okay, we already know that we need these values, so we can just set them. And then we will sample only the remaining variables. The point though is that we need to assign some importance weights. And these represent the probability that the specific event would have been sampled in the particle. Okay, so we're assigning these event variables, but we somehow should say how likely it was to see these events actually. Okay, so let's see it in practice. What is the probability that the person is artificially ventilated? So P of V1. Now use forward sampling to obtain a set of particles, like say M, with event variable y, and then weigh each particle according to the probability that the event y would have been generated in the sampling process. So what do we mean by that? Okay, we know that the ventilation should be set to 1. So we're talking about this value. V0 is not there. It's only V1. But you see that, like, if I can sample a particle, and then if I see that the value of B is B1, for example here, then I say that the weight corresponding to V1 is 0.9, and otherwise it's 0.02. The idea behind this weighting is that if I was doing, for example, forward sampling, how would I sample ventilation? Well, I would first sample B, and based on the value, say for example it's B0. Based on the value I get, then I would sample V1. You can see that if I had B0 here, then the probability that I would end up with V1 is really low. Whereas if I would have ended up with B1, it would be quite high. And these weights are to resemble this. So I don't want to just put like to set the value of V1 to these and then sample the rest of them. And so I will see that, for example, B will end up to be B0, and that can happen frequently. So I would have in many of the instances B0 here, and at the same time I already have V1. This does not represent reality, because the two of them happening together in this conditional manner, it should happen with really a low probability, and the weights are to capture that. Okay, so if I do this, I just do my sampling. V is set to V1, and then I sample the rest of the variables as before. The only thing is that I assign the weights. So whenever I have B0, it will be 0.02. Whenever it's B1, I will have 0.9. And once I have this, I can compute the probability of the event y as before. So here I have, for example, 3 particles, and the answer will be 1 over m times the summation of the number of times that the event of interest happened. But then here, actually, all of these are the event of interest, right? So I need to consider the weight. So rather than here saying how many times, I need to say how many weights, kind of. So here I will say for the first one 0.02 plus 0.9 plus 0.9, and the final answer will be 0.61. Okay? Now, let's make it a little bit more complicated. What if I have 2 variables, M0, C1? Again, we sample a set of particles where y, the event, is set to M0 and C1, and each particle has an importance weight representing how likely it was that M0 and C1 were sampled in the particle. So how do I do this? Well, M0 is not conditioned on any other variable. right? Mask here. So the importance is just P of M0, and it's basically 1 over 3. For C1, though, it depends on its parents. So it will be P of C1 condition on M and D, but here M is set to M0. Okay? Remember the idea that we'll just take out this, cross out these ones that we don't need. So if D0 was sampled in the particle, then the total weight would be this multiplied by this, okay? And where we have instead of D0, and if D1 was sampled, same story, and we can calculate the weights in both cases. The whole point is that the weight for M0 and the weight for C1, they have to be multiplied in each other. So we have a total weight, okay? So I have a number of particles, and I can calculate the weight for each of them. Just note that M is set to M0 and C is set to C1. The other ones are being sampled. Okay, once we do this, all particles are sampled such that they contain the event Y. This data set, the estimated probability of the event Y is just the average of the particle weights as before. So 1 over 4 times the summation of the weights, and we get the final value of 7 over 24. So to write this algorithm that we just explained in example, we have again a topological ordering of X in a Bayesian network of the variables, and Y is the set of event variables. We set W equal to 1. We start from there. And for each node I, we do the following. So we go into each of these variables. If xi is not in Y, it's not in the ones that we have to set its value to something, then we will sample it, similar to forward sampling. And then we will assign that sampled value to xi. Okay? Otherwise, it means that xi is in the event of interest, so we just fit it there. We don't need to sample it, we just assign that value, but then we have to update our weight. So for each variable in Y, we update the weight. We have to multiply it by the probability of xi condition on the parents of xi, where the parents are already assigned from these steps, or from this one. So this is basically a number in the CPD. Okay, and the algorithm can be optimized by restricting I to the ancestors of Y because descendants do not appear in the weights. Now some intuition on the likelihood weighting. We have observed variables and we have sample variables. The observed variables influence the values of the descendants when we're doing the sampling. For example, here, if we have Y1 observed, it influences the value of V2 in the sampling process, right? In the CPD, I only have Y1, the sampled value of Y1. Now, what about V2? How does this one influence the observed events? Well, it doesn't impact the event itself. Like if I have set the value of Y to be equal to Y0 or Y1, we cannot change that, but it impacts the probability or the weight of that variable, okay? So for example here, V2 is the sampled value, the sampled variables, and it influences the probability of Y2 in the computation of the weight W. Okay. So here if I have Y2, which is the observed event, we saw that when calculating the weight of this, I need to go back and check the CPD, which depends on its parent node. So the weight W of a particle contains information about both the values of the event Y as well as the values of the sampled variables. A particle with a higher weight is more important or more worthy and that means that the particle emerges with a higher probability, right? Now let's use the this weighting for conditional probabilities. I mean, that was the main motivation that brought us here. So far, we only saw how to calculate P of y. But we want to see how we can calculate P of, say, C1 condition on M0, given that we have some evidence. Okay, well, we can again use this definition of conditional probability, and we can generate likelihood weighting set D with event Y and Z, where Y and Z are set to C1 and M0, respectively. And then we can redo this for M0 and generate another data set for Z equal to M0. Okay, so this data set is for the nominator, where we have C and M. They are set to these values C1 and M0, and then we only need to sample D, and we accordingly calculate the weight. But then for this one, you may say, why don't we use the same one to calculate Z? Well, if we do that, then for example, we don't get to sample C, right? It's set to C1, whereas here it's free. It can be set to C0. So we need to redo this sampling, at least based on this method, and we obtain another data set. It doesn't need to be the same size of the previous one. We just need another data set, and the weights could be different. And just the point is that here M is the event, so M is set to M0. Okay. So what do we do next? Well, we can use unnormalized importance sampling estimator. What is that? Well, PD, P hat of D, the estimate of this probability, is the average of the weights assigned to the instances. So 1/4 times the summation of these weights. This will give us the probability, the estimate of this C1 and M0, and for M0, the denominator, we will use this data set. Same story. And then we simply divide them. So I get 7/8 here. Okay, that was just an example. In general, if we want to calculate the conditional probability Py condition on Z, the first approach that we just discussed was to first obtain a whole data set where Y and Z are conditioned both as the event, and then another data set where just Z is considered as the event, and then we use the ratio likelihood weighting estimator, which is to take the average of the weights in each of these data sets and then divide them by each other. So in this case, unnormalized importance sampling is used for both the nominator and the denominator. There's another approach, and that is first we obtain the joint distribution of Py condition on Z by generating a set of likelihood weighted particles. So in this case, we look, the difference is that here this is capital Y, so it's a joint distribution conditioned on the event Z. You may say, why is it called joint? It's not just called condition. It is condition, but we're interested in this Y part, and this is different from what we had here, which is just an event, a single value. It's the all possibilities here. So if I have the joint distribution, then I can use normalized likelihood weighting estimator. And that is, if I want to consider to find this particular value of small letter y compared to this general joint distribution, then I can just do the likelihood weighting as before, which is summing over the weights of each particle that matches. So I have a number of particles here, and I should just see for each one whether they match or not the event of interest, small letter y. If they do, then I include the weight, and then I add all of them up. In the denominator, I will just have all of the weights, and then I'll do the division. Okay, what is the intuition of likelihood weighting? There is a separate section for this. Thanks for your attention.